Hello everyone, this is Haobeng Wang from Lancaster University, and today I'm going to talk about my work on HeadShift, head pointing with dynamic control display game. This work was done with my colleague Ludwig Sidemark, Florian Weidner, Joshua Nguyen, and my supervisor Hans Gallison. Head pointing is commonly used as a spatial input technique for 3D interactions. With a head-mounted display, we have a cursor that's fixed one-to-one at the center of the field of view, coupled with head vector. To point at a target, we rotate our head and align the viewport center to the target. This is very simple and intuitive. However, this has a problem of limited precision, especially for small targets and requiring exaggerated head movement to point at target far away. Also, it is unnatural because we only turn our head as far as necessary to bring a target into the view during the natural viewing process, instead of fully aligning our head to the target. In HeadShift, we integrate pointing acceleration into head pointing via dynamic control display game. As you can see, the cursor is decoupled from the center for pointing. It goes ahead from the viewport center for fast reaching the target and then slows down for refinement. At the same time, the cursor offset is controlled in a comfortable viewing range during the selection. We conducted a performance evaluation with a physical task across different amplitudes and width, with 3 variations of HeadShift, low, medium, and high, against the baseline 1-to-1 for all referred as no gain in our study. After this, we also conducted a usability evaluation with 3 applications, comparing the best performed version of HeadShift against 1-to-1 in 3 aspects. This covers free and random selections in 2D, vertical placement, that frequently picking up tools on the ground and sorting them into tool sets on the wall, and precise horizontal docking, in which participants pick up a piece of furniture in the menu and precisely dock them into outlines in 3D space. A quick summary of the results. The main performance benefit of HeadShift is lower error rate or increased precision of input. This is significant for interaction in 3D where recast input is limited in accuracy. Second, the technique makes target selectable at a natural offset from the head. This reduces effort and avoids exaggerated head movement for alignment of the viewport with the target. Lastly, HeadShift reduces the overall range of neck rotation required for reaching targets. This improves ergonomics and can help avoid neck strain while increasing the interaction range, for example, in seated interaction in 3D environments. Beyond the specifics of HeadShift, we would like to share some insights with you during our development process. So if you remember, we've talked about at the beginning, when pointing acceleration is applied to head pointing, the cursor is decoupled from the view. So the first point I want to make here is we look at the pointer during head pointing. This may sound like of course and stupid point to make, but it was not a problem at all if we just fix the cursor at the center and just assume eye gaze as the same as the head vector. However, when the cursor is decoupled here, because our eyes are following the cursor cannot be offset too much from the vector or the head vector. This is because in the natural visual process, eyes would not normally deviate from the head vector for 15 to 20 degrees. If this range is exceeded, it will be uncomfortable, and we'll also observe participants in the pilot test were pointing in a weird eye-head angle and head postures like this, or this. In HeadShift, we applied an offset control to the cursor that limits the cursor in a comfortable viewing range, and we found this improved both performance and user experience. The other point I want to share is also on eye-head coordination in head pointing. So going back to this graph, you can see the comfortable viewing range is not horizontally symmetrical, but instead have a downward bias. This means that we are more comfortable with looking downwards than upwards. As a result, we slightly amplified the downward cursor movement so that the cursor is more likely appear at the lower half of the horizon, which is more comfortable for viewing. In summary, with HeadShift, we propose an improved head pointing technique with enhanced performance and user experience, and this lies in high precision, reduced effort, and improved ergonomics. The technique is generalizable across HMDs and adaptable to other types of displays, with no target assistance needed and only takes head as input. From the specifics of HeadShift, we propose a design principle that head pointing with city gain need to integrate eye-head coordination into the design of transfer functions. Okay, thank you very much for your attention, and of course we have more insights to share with you, such as head movement kinematics during aimed movement, and how to design city gain functions for incorporating different head movement features, asymmetricity of vertical head movement, how we tune transfer functions, and choosing of use first order or second order control in the design. For all these details, please check the paper, and you are also very welcome to chat with me in person or via email. Thank you very much again, and see you.